interpretations of the differences between relativistic quantum field theories and non-relativistic quantum field theories. So in the first part, I'm going to talk about a received view, which claims that relativistic quantum field theories do not admit particle interpretations. I'll argue that the concept of particle that informs this view is motivated by non-relativistic intuitions associated with the structure of classical spacetimes, and that should be abandoned. And I'll briefly review an example of a non-relativistic quantum field theory that consistently incorporates gravity, what's been called Newtonian quantum gravity. I'll then consider what the existence of such a theory suggests about the relations between theories in physics, and in particular about possible ways of constructing a fully relativistic quantum theory of gravity. So, by a relativistic quantum field theory, I'm going to mean a quantum field theory invariant under the symmetries of a Lorentzian spacetime. And by a non-relativistic quantum field theory, I'm going to mean a quantum field theory invariant under the symmetries of a classical spacetime. So a quick review. Lorentzian spacetimes are the arena for relativistic quantum field theories, and they can be represented by a collection of points given by a differential manifold that's endowed with additional structure that's encoded in a pseudo-Riemannian metric of Lorentzian signature. And the metric satisfies a compatibility condition that determines a unique curvature tensor. So, one example of a Lorentzian spacetime is Minkowski spacetime. Of course, it's characterized by a vanishing curvature tensor. And recall that the structure of Minkowski spacetime entails there's no unique way to separate time from space. So any two observers moving inertially with respect to each other will disagree on the time interval between any two events and the spatial interval between any two events. And the structure can be included in a symmetry group, point gray group, and it's generated by vector fields that annihilate the Minkowski measure. So another example of the Lorentzian spacetime is vacuum Einstein spacetime, characterized by a vanishing Ritchie tensor. And this entails spatio-temporal flatness only in conformally flat Lorentzian spacetimes, those in which the Weyl curvature tensor vanishes. So, different Lorentzian spacetimes have different metrical structure and hence different curvature, but all are characterized by the same Lorentzian signature. And one can show that this entails that all Lorentzian spacetimes are isomorphic, look like Minkowski spacetime is small. And so more precisely, the tangent space at every point in a Lorentzian spacetime is isomorphic to the Minkowski vector space. So we might say that locally, a Lorentzian spacetime has the structure of Minkowski spacetime. And corresponding to different types of Lorentzian spacetimes, there can be different types of relativistic quantum field theories. Some in flat Minkowski spacetime and others in curved Lorentzian spacetimes. Now compare Lorentzian spacetimes with classical spacetimes. The classical spacetime, again, can be represented by a collection of points endowed with additional structure, but in this case, the structure is encoded in three objects, a spatial metric, a temporal metric, and a derivative operator. And these objects are required to satisfy orthogonality and compatibility conditions. But unlike the Lorentzian case, the compatibility condition fails to uniquely determine a curvature tensor. While all classical spacetimes have the same metrical structure, they may differ on their curvature. But the common metrical structure entails that in any classical spacetime, there's always a unique way to separate time from space. So any two inertial observers will always agree on the time interval between any two events and the spatial interval between any two simultaneous events in a classical spacetime. All classical this structure can be included in a symmetry group, and you can define the symmetry group that all classical spacetimes have in common, even though they may differ on additional symmetries. and this group is generated by vector fields that annihilate the spatial and temporal metrics. So, one example of a classical spacetime is Newtonian spacetime, which is spatio-temporally flat. And its symmetry group is the Galilei group, which is generated by vector fields that annihilate the spatial and temporal metrics and the connection associated with the flat curvature. Another example of the classical spacetime is Maxwellian spacetime, characterized by the vanishing of the rotational part of the curvature tensor. And its symmetry group is given by the Maxwell group, which is generated by vector fields that annihilate the spatial and temporal metrics and the rotational part of the connection. So again, different classical spacetimes have the same metrical structure, but different curvature, and all are characterized by absolute spatial and temporal metrics. And corresponded to different types of classical spacetimes, there can be different types of non-relativistic quantum field theories. And some in flat Newtonian spacetime, and others in curved classical spacetimes. So, I'd now like to consider how this spatial-temporal distinction between relativistic quantum field theories and non-relativistic quantum field theories impacts the current debate in the philosophy of quantum field theory, and with debate over particle interpretations. So, according to a received view, in order to admit a particle interpretation, quantum field theory must satisfy the following two conditions. First, the quantum field theory must admit a Fock space formulation in which local number operators appear that can be interpreted as acting on the state of a system associated with the boundary region of spacetime and returning the number of particles in that region. And secondly, the quantum field theory must admit a unique Fock space formulation in which a total number operator appears that can be interpreted as acting on the state of the system and returning the total number of particles in that state. So condition A is supposed to encode the essential particle characteristic of localizability. For a system of particles distributed over various regions of space, an adequate theory must be able to identify the number of particles located in each region. And condition B is supposed to encode the essential particle characteristic of countability. For a system of particles distributed over various regions of space, an adequate theory must be able to identify the unique value of the total number of particles counted over all regions. So it's fairly simple to demonstrate that conditions A and B fail in relativistic quantum field theories. So first consider condition B, requirement of a unique total number operator. So in general, condition B faces the problem of privilege, namely relativistic quantum field theories admit unitarily inequivalent Fock space formulation, Fock space representations of their canonical commutation relations. Consequence of the failure of the Stone-von Neumann theorem for relativistic theories with infinite degrees of freedom. So to the extent that unitary equivalence is necessary for physical equivalence, this suggests that any given relativistic quantum field theory admits many different ways to parse particle talk, one for every unitary equivalence class of Fock space representations and their attendant total number operator. Well, this problem of privilege may appear to be solved in Minkowski spacetime by appeal to the time-like isometry subgroup of the Poincare group. So intuitively, the time-like symmetries of Minkowski spacetime provide one with a way to split the frequencies of solutions to relativistic field equations. And this allows the construction of a one-particle state space on which a Fock space representation can then be built. And Kay showed that this method of constructing a Fock space representation is unique up to unitary equivalence. But the Unruh effect, in one guise, suggests, at least to some authors, that relativistic quantum field theories in Minkowski spacetime do not avoid the problem of privilege. So when the time-like isometry subgroup of the Poincare group is restricted to a portion of Minkowski spacetime, it's called the right Rindler wedge. it admits two distinct time-like killing vector fields, one associated with inertial frames and the other with accelerated frames. And this gives rise to two unitarily equivalent Fock space representations, the standard Minkowski representation and the Rindler representation. And this has suggested to some authors that inertial and accelerating observers will disagree over the particle content of a relativistic quantum field theory in Minkowski spacetime. But to other authors, the fact that the right Rindler wedge is extendable, the fact that it can be embedded in a larger spacetime, makes it physically inadmissible as an arena in which to define a relativistic quantum field theory. So to these authors, the Unruh effect is not a problem per se in condition B. But in any event, Haag's theorem blocks condition B for realistic, in other words, interactive relativistic quantum field theories. So under a reasonable assumption, Haag's theorem entails that representations of the canonical commutation relations for both non-interactive and an interactive relativistic quantum field theory cannot be constructed so that they are unitarily equivalent at a given time. So provided, again, that unitary equivalence is a necessary condition for physical equivalence, this suggests that an interactive relativistic quantum field theory cannot be interpreted as consisting of a system of initially non-interacting particles that interact over a finite period of time and then separate into, back into non-interacting states. A typical scenario for scattering experiments. But more precisely, Haag's theorem suggests that a Fock space representation of the canonical commutation relations of a non-interacting relativistic quantum field theory cannot be used to represent particle states in an interacting relativistic quantum field theory. Well, one might then wonder if particle states might be represented more directly in an interacting relativistic quantum field theory by constructing an explicit Fock space representation of its canonical commutation relations, as opposed to piggybacking on non-interacting representations. However, it's unclear if such a Fock space representation of the canonical commutation relations for an interacting relativistic quantum field theory can be constructed. So I conclude, what normally concludes that condition B fails in relativistic quantum field theories. Because that's the conclusion of this. So, condition A, the requirement of local number operators. Condition A is spoiled in relativistic quantum field theories in the following way. First, consider the separability corollary found in Schlieder and Whiteman. So let A be a local algebra of operators associated with the bounded region of spacetime. If following three conditions are satisfied, the vacuum state is cyclic for A, what might be called local cyclicity. The spacetime region has non-trivial causal complement and relativistic local commutativity holds. Then the vacuum state is separated for local algebra. In other words, any operator in the algebra, for any operator in the algebra, if it annihilates the vacuum, then it's identically zero. So the Reeh-Schlieder theorem secures condition 1 for Minkowski spacetime. The structure of Minkowski spacetime secures condition 2, and relativistic quantum field theories satisfy relativistic local commutativity condition 3. Thus, the vacuum state of a relativistic quantum field theory in Minkowski spacetime is separated. The annihilation operators that appear in Fock space formulations of quantum field theories by definition annihilate the vacuum and act non-trivially on other states. So separability of the vacuum entails that there can be no annihilation operator associated with the bounded region of Minkowski spacetime. Thus, there can be no number operator associated with such a region, and that number operators are defined in terms of annihilation operators. Thus, local number operators in the sense of condition A cannot exist for relativistic quantum field theories in Minkowski spacetime. So much for Minkowski spacetime, but what about Lorentzian spacetimes in general? question now arises as to what extent does the separability corollary hold for relativistic quantum field theories in Lorentz spacetimes, particle compressed spacetime? Well, extensions of the Reeh-Schlieder theorem have been proven for relativistic quantum field theories in ultrastatic and stationary Lorentzian spacetimes. One of these authors states the following, Strohmeyer. As soon as a classical field satisfies a certain hyperbolic partial differential equation, a state of the field algebra of the quantized theory, which is a ground or continuous state with respect to the group of time translations, has the Reeh-Schlieder property, what I call local cyclicity. Well, this might suggest that local cyclicity of the vacuum is a generic feature of relativistic quantum field theories in globally hyperbolic Lorentzian spacetimes. But if this is right, then local cyclicity is not a generic feature of relativistic quantum field theories in Lorentzian spacetimes. Fuster and Higuchi demonstrated that global hyperbolicity is not a necessary condition for the existence of a relativistic quantum field theory or Lorentzian spacetime. I think the idea here is you can, for any point in a relativistic, for any point in the Lorentzian spacetime, you can define a neighborhood of that point that is globally hyperbolic, and you can associate a local algebra of operators with that neighborhood. And then the idea is to piece together the local algebras associated with these globally hyperbolic neighborhoods of points into a global algebra. And apparently, in some cases, the global algebra has the correct properties that define a relativistic quantum field theory. Now, note also that in Strohmeyer's comment, the reference to be in a ground or KMS state with respect to the group of time translations is a reference to the state being analytic and being energy. And such analyticity might be identified as a necessary condition for local cyclicity. However, as I'll discuss in just a moment, for local algebras defined on spatial regions of classical spacetimes, local cyclicity fails, even though, assumedly, the vacuum state is analytic in the appropriate sense. Thus, it appears that analyticity isn't sufficient for local cyclicity either. So, in general, local cyclicity is not a generic feature of analytic states. Let me move on to non-relativistic quantum field theories. Now, in non-relativistic quantum field theories, both free and interactant conditions A and B of the received view are satisfied. I'm going to try to argue that this is due to the presence of an absolute temporal metric in classical spacetimes. So, consider condition A first. Well, any chance of extending the separability corollary to non-relativistic quantum field theories first requires replacing the requirement of relativistic local commutativity with its non-relativistic analog. Non-relativistic local commutativity requires that field quantities associated with space-time regions with zero temporal and non-zero spatial separation commute. And this requires keeping track of the distinction between local algebras defined on spatial temporal regions of space-time and those defined on spatial regions. Now, for spatio-temporal local algebras associated with non-relativistic quantum field theories, report demonstrated local cyclicity in the vacuum. But the absolute temporal structure of classical spacetimes entails that the causal complement of a spatio-temporal region of a classical spacetime is trivial. So vacuum separability fails in this case. And for spatial local algebras associated with non-relativistic quantum field theories, local cyclicity of the vacuum does not hold. So vacuum separability fails in this case too. Now, why does local cyclicity fail for local algebras associated with spatial regions of the classical spacetime? Well, here's my conjecture. This This is based on remarks made by Saunders and Streeter. So suppose phi is a positive frequency solution to a well-posed partial differential equation. And it turns out that phi is a boundary value of a holomorphic function defined on a super extension of the real number line. Now let S be an open spatial region of space-time. If phi vanishes on S, then it vanishes in the domain of dependence of S. Now consider the case of a hyperbolic partial differential equation in other Lorentzian space-time. The domain of dependence of S will in general have non-zero temporal extent. You can think of this as a result of the prohibition on indefinitely large propagation speeds in Lorentzian space-time. So if phi vanishes on S, it vanishes on in an open set in time, and the edge of the wedge theorem then entails that it vanishes everywhere. So if phi is non-zero somewhere, it cannot vanish on S. And this property of the solution to a partial differential equation is what Siegel and Goodman referred to as the anti-locality on spatial regions of the differential operator associated with the PDE. And Siegel and Goodman demonstrated that such anti-locality entails the vacuum state of a relativistic quantum field theory defined on the space-time as locally cyclic. Now consider the case of a parabolic PDE in a classical space-time. So due to the absolute temporal metric, the domain of dependence of S will have zero temporal extent. Think of this as a result of a lack of a prohibition on indefinitely large propagation speeds in a classical space-time. So if phi vanishes on S, then it need not vanish on an open set in time, and hence phi being non-zero somewhere is consistent with it vanishing on S. So anti-locality for spatial regions fails, and assumedly local simplicity does too. So to recap, the conjecture here is that the presence of an absolute temporal metric guarantees that the vacuum of a non-relativistic quantum field theory is not locally cyclic for spatial local algebras, and thus it's not simple. So moving on to condition B in non-relativistic quantum field theories. In non-relativistic quantum field theories, there's no problem with privilege. In particular, the absolute temporal metric of a classical space-time guarantees a unique global time function on the space-time. And this guarantees a unique means to construct a one-particle structure of the classical phase space, hence guaranteeing a unique total number operator. Unitarily inequivalent representations of the canonical commutation relations may still occur if the classical phase space has topological defects, even in systems with finite degrees of freedom, and assumedly unique local time functions. But barring such mutants, the point goes through. So, the general moral I draw from this part of the talk is the following. To the extent that conditions A and B require the existence of an absolute temporal metric, they are informed by a non-relativistic concept of time, and thus are inappropriate and informed in interpretations of relativistic quantum field theories. Now, I'd like to now consider a concrete example of a non-relativistic quantum field theory in a curved classical space-time. And to set the stage, I'd first like to review two types of classical Newtonian gravitation theory. It turns out that it's a second type that admits a quantization. So here's the first type. This type is formulated with the gravitational potential against the backdrop of a fixed classical space-time, and can be represented by models that include a differentiable manifold with spatial and temporal metrics, a derivative operator, and scalar fields that represent the Newtonian gravitational potential field capital Phi and the mass density rho.
You want the indices up on that H in the final line motion.
What was the comment?
In the final equation, the H on the right side, you want to present this example.
Yeah. So the metrics and connection define a classical space-time, and the potential field and mass density are required to satisfy the Poisson equation and the equation of motion. Now recall that to fully specify a classical space-time, one has to pick out a particular metric-compatible derivative operator, and this can be done by imposing constraints on the curvature tensor. Thus, there can be different versions of this type of Newtonian gravitation theory, dependent on these additional curvature constraints. So, one example might be called neo-Newtonian Newtonian gravity. This is the standard way Newtonian gravity is formulated. So this theory describes Newtonian gravity in terms of a potential field and a mass density defined in spatio-temporally flat neo-Newtonian spacetime. Now a second example can be had by imposing a boundary condition on neo-Newtonian gravity that forces the gravitational potential to vanish at spatial infinity. And the result is a concentration of mass in the center of the universe, in what's been referred to as an island universe effect. And finally, a third example is obtained by defining the Newtonian gravitational potential and mass density in Maxwellian spacetime. All right, now we move on to the second type of classical Newtonian gravitational theory. And this type subsumes the gravitational potential field into the space-time connection and is generally referred to as Newton-Cartan gravity, NCG. So models of NCG eliminate the Newtonian gravitational potential. Now, the spatial and temporal metrics and a compatible derivative operator still define a classical space-time, but the Poisson equation is now replaced by a generalized Poisson equation, and the equation of motion is replaced with the geodesic equation. Now, these changes enforce the principle of equivalence in Newton-Cartan gravity. So intuitively, a Newton-Cartan connection can't distinguish between straight inertial trajectories and curved gravitationally accelerated trajectories. So in this sense, gravity is geometricized. Now, there are different ways this geometrization procedure can be carried out, dependent on additional constraints one imposes on the curvature tensor to specify a particular classical spacetime. So one example might be referred to as weak Newton-Cartan gravity. In this example, the additional curvature constraint imposes what's been referred to as a curl-free condition on the curvature tensor. And this is necessary in recovering weak Newton-Cartan gravity as the non-relativistic limit of general relativity. It imposes a Riemannian symmetry on the curvature tensor that allows you to recover a pseudo-Riemannian that allows the weak Newton-Cartan curvature tensor to be recovered in the non-relativistic limit from a pseudo-Riemannian. The curvature tensor associated with general relativity. Now, this curl-free condition is also necessary but not sufficient in recovering the Poisson equation. And if you want to fully recover the Poisson equation, it suffices to impose a boundary condition on weak Newton-Cartan gravity in the form of asymptotic spatial flatness. Now, arguably, this theory is empirically equivalent to the theory of ungeometricized Newtonian gravity and neo-Newtonian spacetime with the island universe boundary condition, insofar as both theories have the same spatio-temporal and dynamical symmetries appropriately construed. Now, a third example of Newton-Cartan gravity is what might be called strong Newton-Cartan gravity. Here, in addition to the curl-free condition, one imposes a rotation standard, same standard in Maxwellian spacetime. And this is also sufficient to recover the Poisson equation. And one can argue that this theory is empirically equivalent to the theory of ungeometricized Newtonian gravity Maxwellian spacetime, given that one under a certain rule of spacetime and dynamical symmetries. Now it's this last example that generates what's been referred to as Newtonian quantum gravity. So Joy Christian, in a paper published in 1997, demonstrated that the curvature conditions imposed by strong Newton-Cartan gravity are sufficient to recast the theory as a constrained Hamiltonian system. The reduced phase space consists of variables encoding matter degrees of freedom and variables encoding dynamical degrees of freedom in the strong Newton-Cartan connection. And these latter are identified as gravitational degrees of freedom. The phase space has a non-degenerate symplectic structure and a unique one-parameter family of time evolution maps due to the absolute temporal metric. So it admits a unique one-particle structure and thus a unique Fock-based representation of the commutation relations. And so the result is Christian's Newtonian quantum gravity, NQFT. So it takes the form of an interacting Maxwell invariant quantum field theory set in a curved classical spacetime, what might be called strong Newton-Cartan spacetime. Now, as a non-relativistic quantum field theory, it satisfies conditions A and B of the received view, the received view's notion of particle. And it's interesting to compare it with attempts to construct, standard attempts to construct relativistic quantum field theories of gravity. So, its gravitational degrees of freedom are dynamic, and this distinguishes it from the program of constructing relativistic quantum field theories in curved Lorentzian spacetimes. This program attempts to construct relativistic quantum field theories that incorporate gravity by treating gravity classically as a manifestation of spacetime curvature. And this is done by breaking the dynamical link between spacetime and matter given in general relativity. And the curved Lorentzian spacetime in such a theory is absolute in the sense that it has no dynamical degrees of freedom. So in Newtonian quantum gravity, on the other hand, strong Newton-Cartan spacetime has quantized dynamical degrees of freedom, namely those associated with the connection. And moreover, again, in Newtonian quantum gravity, we don't face the problem of privilege in determining a Fock-space representation of canonical commutation relations. And this is in contrast to the program of relativistic quantum field theories in curved Lorentzian spacetimes, for which there isn't even a guarantee that the spacetime will admit time-like isometries in the first case. And one can also compare Newtonian quantum gravity to the program of semi-classical quantum gravity. The fact that the gravitational degrees of freedom in Newtonian quantum gravity are fully quantized distinguishes it from semi-classical approaches to incorporating gravity into relativistic quantum field theories. Semi-classical quantum gravity attempts to include dynamical degrees of freedom associated with the gravitational field into a relativistic quantum field theory by replacing the stress energy tensor in the Einstein equation with its expectation value with respect to quantized matter fields. So in semi-classical quantum gravity, one treats gravity classically, and that isn't quantized. But one quantizes the matter fields. Well, Newtonian quantum gravity has suggested to Christian a novel route to formulating a fully relativistic theory of gravity, namely relativizing a non-relativistic theory of quantum gravity. So in the remainder of my talk, I'd like to review this strategy and expand on Christian's picture of intertheoretic relations associated with it. So this part of the talk is a bit more speculative. So to begin, Christian views Newtonian quantum gravity as a means to fill a void in what he refers to as the great dimensional monolith of physics. It's a diagrammatic representation of the relations between fundamental theories of physics. So it takes the form of a cube with axes represented, the Newtonian gravitational constant G, Planck's constant h bar, and the inverse speed of light. And the vertices are meant to represent so classical mechanics, special relativity. This is in Christian's terminology. Galilean invariant quantum mechanics, relativistic quantum field theory. And at the top, when gravity is turned on, Newtonian, Newton-Cartan gravity, general relativity, Newtonian quantum gravity, and the elusive, fully relativistic quantum gravity.
Where's Galilean quantum field theory?
Where's
Galilean quantum field theory.
it's not there. That's one of the modifications. This is Christian's diagram is a modification of a diagram that appeared in a couple of articles by Roger Penrose. Penrose's diagram is a whatever term tetrahedron.
Can't the QM vertex include quantum field theory too? No? So why does that diagram imposed by theory?
That's one of my criticisms.
I mean, why can't I simply write NQFT on that vertex?
Well, now I'd like to investigate some of the limited relations here, and attempt to see how, in particular, non-relativistic quantum field theories can fit into this picture. Just to get back to this diagram, general relativity, for instance, is a theory in which gravity and relativity are turned on, and quantum effects are turned off. So the cube entails that there are three distinct approaches to constructing a fully relativistic quantum theory of gravity. Quantize in general relativity, turning on quantum effects, general relativity, turning on gravity in the relativistic quantum field theory, or and the approach novel to Christian of relativizing Newtonian quantum gravity. I'd now like to briefly consider the nature of the limits in this diagram. So first, the non-relativistic limit might initially be thought of as a contraction of the Poincare group to obtain the Galilei group. An article by Thackeray and Leblanc explicitly demonstrates how this can be done. However, as authors like Brown and Holland indicate, the exact nature of such a non-relativistic limit sometimes depends on the form of the dynamical equations of the relativistic theory, and not just its kinematical group theoretic structure. And moreover, even at the kinematical level, identifying relativistic theories with the Poincare group and non-relativistic theories with the Galilei group is problematic. For instance, the link between general relativity and Newton-Cartan gravity cannot be described in these terms. On the one hand, the Poincare group is not the symmetry group associated with general relativity. Most people identify diffeomorphisms on the manifold as a symmetry group of general relativity. And on the other hand, the version of Newton-Cartan gravity that is the non-relativistic limit of general relativity is weak Newton-Cartan gravity, and this version does not have the Galilei group as its symmetry. So there are problems with fully articulated the relativistic limit, the non-relativistic limit. Now consider the G goes to zero limit. So one problem here concerns the distinction between Ricci flatness and Riemann flatness. So if turning off gravity in general relativity means setting the Newtonian gravitational constant to zero in the Einstein equation, then the result is Ricci flat vacuum Einstein spacetime, and not Riemann flat Minkowski spacetime. which one would expect to be associated with special relativity. And similarly, set in G to 0 in the generalized Poisson equation of Newton-Cartan gravity or Newtonian quantum gravity should result in a Ritchie-flat classical spacetime and not Riemann-flat neo-Newtonian spacetime, which one would expect to associate with Galilei invariant classical mechanics and Galilei invariant quantum mechanics. And now, finally, consider the H bar goes to 0 limit, and it potentially faces the problem of privilege associated with the quantization procedure. So for a theory of a classical relativistic field with infinite degrees of freedom, the failure of the Stone-von Neumann theorem entails that there are uncountably many unitarily and equivalent representations of the canonical commutation relations of the corresponding quantum field theory. Again, inequivalent quantizations also arise for systems with topologically non-trivial state spaces, regardless of whether they're finite or infinite. But barring these topological mutants, the problem of privilege does not arise for either Galilei invariant quantum mechanics or for Newtonian quantum gravity. And now to the problem of where non-relativistic quantum field theories fit in. So in addition to these concerns over how explicit links in the monolith are to be fleshed out, there's a deeper structural problem. So to make it explicit, consider the link between Newtonian quantum gravity and Galilei invariant quantum mechanics. Newtonian quantum gravity is a non-relativistic quantum field theory of gravity in a curved classical spacetime. So turning off gravity in such a theory should result in a non-relativistic quantum field theory in a Ritchie-flat classical spacetime, and the scope of such a theory is larger than the scope of GQM, assuming the latter refers to finite Galilei invariant quantum mechanics. And moreover, turning off relativity in a relativistic quantum field theory should result in a non-relativistic quantum field theory. And again, the scope of non-relativistic quantum field theory, NQFT, in this context seems wider than the scope of GQM. Non-relativistic quantum field theories are infinite dimensional field theories, and they're invariant of the symmetries of a classical spacetime, which need not be neo-Newtonian spacetime. So, naively, one way to fix these links is to add another axis to the monolith that would represent degrees of freedom. One might let NQM refer to non-relativistic finite dimensional quantum theories of particle dynamics, whereby particle in this context just means finite degrees of freedom. And one might consider NQMs to be the n goes to 0 limit of non-relativistic quantum field theories, where n is degrees of freedom. So if we add this additional axis, then the monolith becomes a hypercube with axes that distinguish between particle and field theories on the n-axis, relativistic versus non-relativistic theories, gravitational versus non-gravitational theories, and classical versus quantum theories. And I'd like to briefly consider how one might describe the links that involve turning off gravity in the field theory in this hypercube. I'm sorry. So here in the diagram here, this is the hypercube, and I'm suppressing the g-axis, and the vertices here, let's see, represent non-relativistic classical mechanics, non-relativistic quantum mechanics, relativistic classical mechanics, relativistic quantum mechanics, and if we let the number of degrees of freedom go to a very large infinity, we get non-relativistic classical field theories, relativistic classical field theories, and there's our vertex that represents non-relativistic quantum field theories, and then we also have relativistic quantum field theories. So let me briefly consider how one might describe the links that involve turning off gravity in a field theory. These links result in the four types of theories that are highlighted here in red. So first, a non-relativistic classical field theory should be the G goes to zero limit of a non-relativistic classical field theory of gravity. And an example of such a theory is asymptotically spatially flat Newton-Cartan gravity. And as I mentioned earlier, one can argue that it is empirically equivalent to the version of Newtonian gravity in neo-Newtonian spacetime in which the gravitational potential is required to vanish at spatial infinity. It's island universe, neo-Newtonian gravity. When gravity is turned off in this latter theory, one expects the result to be a Galilean variant classical field theory in neo-Newtonian spacetime. In other words, an example of a non-relativistic classical field theory. Now, relativistic classical field theory should be the G goes to zero limit of relativistic classical field theories of gravity. And an example of the latter is general relativity. So turning off gravity and general relativity assumedly results in a relativistic classical field theory in a Ricci flat limits in spacetime. And finally, non-relativistic quantum field theory should be the G goes to zero limit of non-relativistic quantum field theories of gravity. And an example of the latter is Newtonian quantum gravity. And its G goes to zero limit evidently should be a non-relativistic quantum field theory in a Ricci flat classical spacetime. So, adding a fourth dimension, a fourth axis to Christian's monolith in this way finally suggests that there should be four ways of turning on fully relativistic quantum gravity. Right? By quantizing general relativity, by turning on gravity in a relativistic quantum field theory, by relativizing Newtonian quantum gravity, or by taking some sort of thermodynamic limit of a relativistic quantum particle theory of gravity. That would be the fourth way. Now, what a relativistic quantum particle theory of gravity would amount to is anyone's guess. So that's all I'm going to talk through.
Two questions. Why in the Cartan theory do you talk about the gravitational big neutrinos dynamic?
I would associate them with the degrees of freedom in the connection. The part of the connection that's dependent on the mass density.
It's a long successor of that theory, but what, as I recall, one of its features is that there are no independent gravitational field freedom that quantities that are more than mass quantities. They don't have to get gravitational waves and they don't quantize the units. No classical gravity. It's not really changing.
I mean, I think here's a way of thinking of it, right? Once you fix the source terms, you fix the connection up to different levels of fragments. And the different markers of fragments take one of that when you go from that.
And that's a feature because I'm pretty sure it's a
Yeah. So it seems like, I mean, if you,
So once you fix the mass density, that fixes the space time.
yeah, and that's not mathematical theory classically, and I'm pretty sure boundary that's one of the big things that that's inside of practice. And the other thing I was going to slightly take issue with in your framework here. I mean, I see it's the attraction saying let's put field theory into a dimension. Of course, if you look at the theories that turn out, one of the theories that turns out there, i.e. relativistic particle mechanics, relativistic quantum particle mechanics, turns out to be pretty hard to do, and it seems not to be a stable kind of theory. I mean, it's not an accident that we went to field theoretic and we went to relativistic quantum mechanics. And I worry that the slight problem of visualizing the problem this way, although I agree with what's later for non-relativistic field theories, is that it kind of loses track of the extent to which the compulsiveness of field theory from discoveries that you want to relatively utilize classical non-relativistic methods. I mean, I think you think things like particle classification.
Yeah, look, I think there are Galilean quantum field theories that model perturbation.
No, I believe it. My point is that you can't do relativistic quantum mechanics of anything but a very trivial kind, unless you allow for theoretic technology.
A couple things. First, I think that I wonder if in your first setup, where you had your conditions A and B, whether it would be a condition C as well. So it seems to me that in the case of a block representation for a system where you have number operators, one of the things that gives us confidence that we're counting particles rather than counting energy lines or something like that is that in the relativistic context, we know that E equals mc squared. So we know, once we know what kind of particle we're dealing with, particular mass, so we know once we apply we know what energies we would expect the end particle states to have. Right? So that gives us confidence that we're not just counting something which is not at all particulate, but we're counting something which we have reason to believe to be particulate. Which is an interesting consideration because that is a relativistic consideration, right? It doesn't map over, I don't think, map over to the
Yeah, I tried to include that instead of adding that as a third condition. I tried to include that as conditions A and B are qualified by saying that, for instance, local number operators have to appear that can be interpreted as acting on states to return the number of particles. So
think about non-relativistic quantum mechanics, so we have ladder operators. Do we think we're counting particles in this? In some instances maybe we do, and some we don't, as a context. Something like that. In some cases you might want to say you're counting energy levels.
We're not counting particles.
You're not counting particles.
We're counting quantons.
yeah, so you're saying there's a constraint in the relativistic case that.
Well, so
that
I don't know if I want to be pushed to say this, but maybe one interesting way of going about this might be to say that when you start with Lorentzian field theory and then you move to the Galilean case, say, even though the formalism is the same, you shouldn't think of yourself as quantum particles.
and there's some condition in the relativistic case that some additional condition that you can impose that would distinguish between a legitimate interpretation of a number operator as a particle operator.
Perhaps,
And
I don't know, I
condition
haven't
doesn't
thought this
exist.
through, but that might be one. The second minor comment was, I thought it was interesting that, I think it was in the context of the Newtonian quantum gravity, you said something about breaking the connection between space-time and matter. Right, and that made me wonder whether that part, so that sounded quite different from what you were saying earlier in the paper, where you were saying that it's the space-time structure, which surely play a critical role, whether you can get number operators by particles, right? But there it seems to be that the particle, the matter, the particles in the space-time structure is in the particle.
Yeah, well, I take it in the Newtonian quantum gravity. I mean, there is an absolute temporal metric, and I guess that my claim, well, my understanding is that provides a unique way to specify that provides a means to specify a unique total number operator. Yeah, but then there's this issue of.
It's just
So
interesting how they happen.
Yeah, I mean, the extent to which the gravitational degrees of freedom are are dynamic in Newtonian quantum gravity. Might be an issue that you're pointing out.
This is like maybe just a question of clarification. Did you say what the worry is about the total number operator in relativistic quantum field theories? Is it that it doesn't exist, or is it that it doesn't have a appropriate kind of spectrum constructed, or it's not unique? What is the word?
It's not unique.
It's not unique. Okay. So, well, I'm not sure what the non-uniqueness amounts to, but why would anybody expect in general the total particle number to be well defined? Why are you on that one? I mean, in an infinite space, this is my intuition. My intuition is that infinite spatial surface you don't necessarily need any more than you think of general energy classically is a well-defined quantity.
Yeah. I mean, I guess naively, you'd want to, I mean, if your theory is supposed to be describing particles, then there should be a fact of the matter how many particles there are.
But if I might comment on that, the working physicist who believes in quantons, I've figured out not to use the P word on this. The working physicist who describes these things never uses the particle number operator, either local or global, except in the asymptotic realm, where for all practical purposes all interactions have disappeared. Now they still want to keep track of the constituents of the system being observed. And what do they use? They use things like total electric charge, total lepton number, total baryon number, isotopic spin, strangeness, quantities which to one degree or another are conserved dynamically and can be used indirectly to infer numbers of constituents. But you never pay attention to the number of constituents while the interactions are going on, because that number, aside from the fact that it's changing wildly, it's even wildly undefined. It has statistical indefiniteness, quantum mechanical statistical indefiniteness. So this is not a criticism of your approach idiosyncratically, because I know that this approach, this focus on number operators is sort of pandemic in the literature. But it does strike me as rather distant from the practice that is employed by physicists who use quantum field theory.
Do you want to continue with the question? Is that your next thing?
Oh, me?
Yeah.
Oh, no, that was it.
That was it.
Okay.
So I'm trying to understand what the G goes to zero limit means. I mean, if I just think of G as the thing that multiplies the stress energy in Einstein's equation, then yeah, you just get Ricci flat. But if I think of, 1/16 pi G as the thing that multiplies the scale of curvature in the action which goes into the path integral, then I could imagine very different consequences for taking G goes to zero limit. So is there a nice sort of simple story about, what the G goes to zero limit means and why it behaves in a particular way?
Yeah, not that I'm aware of. I'm not sure how to formulate what it means to turn off gravity, for instance. Well, that's sort of one of the questions I raised in the talk that I leave unanswered.
But on your cube, you had things like, okay, we take these theories and then we take G goes to zero and we get these theories. So that's well understood, or
No, I don't know. It's Christian's cube.
Okay.
So going back to the very first part of the talk about quantum. Did I get the logic of this right? So people say, if the particle, then sort of X, A and B were the conditions, and you're and then they say not X, and then sort of conclude not particles. And you're criticizing that by saying we could infer instead that the conditional is wrong, that X isn't a necessary condition for particles. Is that the logic of it?
Yeah, I think so. I'm calling into question the necessary conditions.
So we suddenly have, okay. So how are we going to settle that issue? I guess I didn't quite get how we're supposed to settle that issue, whether it's right to keep the conditional and infer they're not particles, or reject the conditional.
Yeah,
Because in a certain sense, the results you're talking about are just more risk for the mill of showing they're not particles, right? If you hold on to the condition.
yeah. I guess that's one way you can interpret it. I mean, I guess.
So I guess what I was waiting for in the rest of the talk was some other kind of characterization of particles that you found in the
Yeah, I
Newtonian
know.
case to say, but look, we get this in the quantum case, and so that's a good reason to reject the necessary condition.
Yeah, I'm not offering an alternative. But
So yeah, so your reason for criticizing them as necessary conditions is because they rely on sort of classical intuitions and an absolute temporal structure. But then, so you're whatever proposing for a different condition would presumably not have that. Do you have any? Is this something you have ideas about that just weren't part of the talk, or just?
Nothing worked out. Yeah, I mean.
But that doesn't seem like a criticism of the condition. It just seems to show why the condition fails and why we don't have particles. I mean, if you looked at it from that side.
So I was sort of thinking, so Maxwellian electrodynamics is a field theory that's special relativistically is beyond that part of the computer sort of like if we imagine four-dimensional objects.
Oh,
It would be on the normal cube, it would have been on the SR point, and then you're going to say it's also on the N goes to infinity point. So, has anyone ever tried to develop either a non-relativistic electrodynamics or a non-field theoretic electrodynamics? I don't really, I'm not sure how useful it would be. It might make a good PhD dissertation, but I don't know.
And the non-theoretic electrodynamics.
Or both, just to see if you could do it.
Yes.
You're doing insight.
That's what we look fine.
Yeah,
Electrodynamics.
One mechanically can't. Induction by the failure of dependencies.
Right.
So slightly better reason.
So on this question of particles, I mean, a while ago, Bill Unruh advocated this radical notion that one should think of particles as just being whatever a particle detector detects, and not assign them any higher reality than that. So is there some reason why we don't want to do that?
Well, I mean, that would allow. I mean, I don't think anything in this talk would argue against that.
Could I make a comment on that?
Please.
It would be very wise, essentially, I think, and I would argue that the founders of quantum mechanics, the Copenhagen School, was initially trying something very much like that, not necessarily restricted to these little constituents, but the idea is to stay close to experimental observation and practice and detection. Now, my guess would be that that by itself would not be adequate to mount a genuine conceptual apparatus, or what I choose to call quantons. But that would be the place to start, and you would never want to lose that connection in the process of elaborating the conceptual apparatus. I think that's exactly the way one has to go.
I mean, kind of following on from that, I guess. I think if we were mistake in thinking about where particles are going to turn up in our QFT to suppose that somehow there's a dichotomy between having them turn up at some level so fundamental we can be past the QFT as fundamentally a particle theory on the one hand, and understanding in purely instrumentalistic terms on the other hand. I mean, and again, apologies for going on about this. The intermediate space where one just has something at an emergent or approximate level, but still takes it perfectly seriously, is all over the place. I mean, in a place where it's typically ungrammatically going on is the particles in physics. And something like a photon, I mean, nobody thinks that a crystal is actually a photon or something. But equally, it doesn't seem helpful to cash out a phonon in purely instrumentalistic detection terms. Phonons are emergent regions inside the crystal which are manifested in certain regimes and functions. And actually, one of the interesting things of what's going on here is why is it that in non-relativistic quantum mechanics we have a possibility of formulating theories where that's not the story to tell about particles, where the particles all the way down, whereas in relativistic quantum mechanics and indeed in solid state physics that doesn't seem to be the story we're telling. And in part of it seems to be to do with relativistic, but in part of it in turn seems to do with the fact that the non-relativistic vacuum doesn't seem to have to be entangled, whereas the relativistic vacuum we know is very thoroughly entangled, and the solid state vacuum, so to speak, is also